This is Mrs. Palmer-Quay with the fourth video for Module 13. In this video I'll be talking about the Gibbs free energy equation and how to use that to determine if a reaction is spontaneous. Let's talk a little bit about spontaneous reactions. The definition for if a reaction is spontaneous is if it will occur under a given set of conditions. If reactants will turn into products, then the reaction is spontaneous. Now, spontaneous reactions can be fast or slow. The only determining factor is if they will actually happen. So some spontaneous reactions are quite rapid, but others are very, very slow. Spontaneous reactions still need activation energy. You still need that energy to get them going, but once, if you just kind of picture that energy diagram in your head, once that activation energy has been put into the system and we've gotten to that transition state at kind of the top of the hill, it's all downhill after that point and the reactions will go ahead and occur. Combustion of paper is a spontaneous reaction, but you do need to put a match to your piece of paper to get it started. And so the match to the paper is the activation energy, but then it will start burning and it'll keep burning until all of the reactant, the paper, has been used up. In physics, free energy is the energy that is available after when an exothermic reaction is going on that can go on to do work, cause motion someplace else. But what you're going to be doing primarily for this course is using what's known as the Gibbs free energy equation. You use this equation to calculate if a reaction will be spontaneous by looking at the enthalpy, the entropy, and the temperature that the reaction is occurring under. This equation you do need to memorize. Delta G equals delta H minus T delta S. And you need to be able to use it. And especially you need to be able to think about it. And we'll get to that in a couple slides. The end answer, where you're going for, is if delta G is negative, then the reaction is spontaneous. Reactions will turn into products if you have plugged in all the numbers and calculated a negative value for delta G. So let's consider the following equation. We have iodine as a solid turning into iodine as a gas. This is known as sublimation. It's not something we've talked about very much in this course, but it is something that happens with iodine. So will iodine sublimate at 35 degrees Celsius? We have some values here. A change in enthalpy for that reaction from a solid to a gas is 39.34 kilojoules per mole. And the change in entropy for that is 86.19 joules per mole Kelvin units. So we need to do some conversion. That needs, from joules, it needs to be turned into kilojoules before you can plug it into the equation. So you start off with our Gibbs free energy equation, delta G equals delta H minus T delta S. And we plug in our 39.34 kilojoules per mole for delta H. And we multiply the temperature, turn to Kelvin units. Be sure that you notice things always need to be in Kelvin units here. And we have converted our joules per mole to kilojoules per mole, so the number gets even smaller. If you go ahead and multiply that all out and finish the equation, you find that delta G at 35 degrees Celsius, or 308 Kelvin units, is a positive 12.8 kilojoules per mole. So the conclusion is that since delta G is positive, iodine will not sublimate at 35 degrees Celsius, which is a good thing because gaseous iodine is poisonous and we really don't want it sublimating if there's any around. It will sublimate at temperatures close to boiling. Maybe if you come back for physics, I'll show you that happening. What I want you to be able to do, though, is really think about the relationship between these different variables in this equation and be able to predict whether a reaction will be spontaneous or not. So consider this. If delta H is negative, if you have an exothermic reaction, and delta S is positive, a reaction is going to more disordered, then you can see that both of those driving forces that cause chemical reactions to happen are moving in the way that encourages a reaction to occur. The energy state is moving from a higher energy state to a lower energy state, and from a more ordered, the entropy is moving from more ordered to more disordered. So when both of those things are going in a direction that will encourage chemical reactions, then delta G will always be negative, and the reaction will be spontaneous at all temperatures. Combustion is an example of that. You are able to light a fire on the top of Mount Everest where it's very, very cold. If you are an extreme explorer, climb up there and need to have some warm tea. Warm, though not hot, because of the high elevation's effects on vapor pressure and boiling. But because it's an exothermic reaction and it is causing more disorder, then this is a reaction that is always spontaneous. But what if that's not true? How about if delta H is negative? It's an exothermic reaction, that's good, and delta S is also negative. It's causing less disorder, something more orderly. Well, then your delta G value might be negative if the temperature is low enough. So when a reaction causes more order to happen, it will be spontaneous at low temperatures. And so the freezing of ice is an example of that. As this ice freezes on the twigs, it is an exothermic reaction. It's giving off little bursts of heat, but the reaction itself, forming solid ice out of liquid water, is more orderly, and so it needs low temperatures in order to proceed. Farmers use the exothermic part of freezing to try to preserve crops in times of frost. We're getting to a kind of a frosty time of year, and strawberries and peaches might be in danger of the blossoms being harmed or the early fruit being harmed. And so one of the techniques that farmers will use is to spray water on plants when freezing temperatures are predicted in late spring days or nights. And as the water freezes on the plant, it is an exothermic reaction, so it is giving off heat and warming the plant so that the plant tissue doesn't freeze. And so then it provides a layer of insulation after that ice is on there. So ice is an example of where your exothermic reaction is combined with a more ordered state, but it will happen at low temperatures. How about the opposite of that? How about if delta H is positive, it's an endothermic reaction, and delta S is also positive, so the reaction leads to more disorder. Then again, your delta G might be negative depending on the temperature. These types of reactions are spontaneous at high temperatures, and high here is a relative term because ice melts. Ice melting is a good example of this. It has to absorb energy from the environment. Energy has to come into that ice cube for it to melt, but as the solid ice turns to liquid water, it becomes more disorderly. Entropy increases. And the high temperatures we're talking about here are room temperature to us, but in the chemical world, these are high temperatures. Cold packs are another good example of how you can have an endothermic reaction that is creating more disorder and occur at warm temperatures. Finally, if your delta H is positive, if it's an endothermic reaction, and delta S is negative, it leads to less disorder or a more orderly reaction, then delta G will always be positive and the reaction will not occur. This is a non-spontaneous reaction. Of course, I can't have a picture of that, so we just have an illustration that you will not be chased by a ball rolling uphill. This reaction will not occur. It is not spontaneous. Here's a little bit of extra stuff. We're going to get into equilibrium in the next module. We've talked about delta G being negative, that the reaction will be spontaneous if delta G is negative, and if it is positive, the reaction will not be spontaneous. So where is delta G 0? Well, delta G is 0 at equilibrium, where the rate of the forward reaction is equal to the rate of the reverse reaction. And we'll get into talking about how a chemical reaction won't go to use up all of the reactants. It will not go to completion unless you do something to it. If you just put, say, two solutions that would react together into a beaker, they will react up to a certain point, and then we'll get to this place that's called equilibrium, where you're not going to have any more reactants turned into products. In fact, the products will be returning back to reactants at the same speed And so at that point, your Gibbs free energy is 0. It's sort of the lowest energy place to be, and that is known as equilibrium. So this is a little advanced notice on what's happening in our next module. This finishes up the videos for Module 13.